So good day and welcome to today's webinar. My name is Matthew McKnight. I'm a technical specialist working for Autodesk out of our Melbourne office, and today's topic is troubleshooting nonlinear analysis in Nastran InCAD. So this follows on from a lot of the other webinars that we've done, many of you of which you'll be able to find on the YouTube channel, the Autodesk ANZ YouTube channel. And this one follows on from that. In today's session, let's have a look at the topics for discussion. We'll be firstly looking at how model settings and how they can contribute towards issues with our nonlinear analysis. We'll talk about parameters. We'll then look at some of the error messages associated with the issues that we might be having in our nonlinear analysis. We'll run through a quick demo to show you what that environment's like. Acknowledge the people who have contributed to the creation of this webinar, and then close up the webinar with any questions that anyone might have. So let's just jump straight into it. So initially, for a lot of our Nastran InCAD users, they're probably going to start out with a linear analysis, set up a linear study, and then transition over to a nonlinear setup. So what I'm going to do is point out to you some of the things that you need to be aware of when you are setting up that study. And firstly is the nonlinear setup area. And this is where, once you've defined the study, where you can define the way that the nonlinear study will be run. It includes things like the number of increments, whether you want to use an intermediate output, the name of the study and the likes, and also some advanced settings. So if we look at a couple of these in isolation, firstly the intermediate output and the number of increments. Number of increments means the number of steps essentially that will be taken in solving the study. So we'll take the loads, it'll apply a portion of the load based on the number of increments that you would like to run, and it will incrementally adjust that until the complete load is applied. And the intermediate output option gives you the ability to be able to output the result, the converged result increment of each of those increments. You will see it dynamically updating on your screen as the analysis is run, and then at the end, once the study has been run and completed, you'll then get the ability to be able to look at the results at each increment as well. So you'll be able to adjust there, look at stresses, strains, displacements, and the likes. Arc length, this is typically turned off by default, as is intermediate output, which can be turned on. Arc length is predominantly used in analysing snap-through of nonlinear problems. So in most instances it won't need to be adjusted, but if you are using snap-through, you can also turn on the arc length option. If we look at some of the advanced settings, and the advanced settings are simply accessed by clicking the advanced settings button on the previous dialog box, you'll be shifted into this environment where you're given a number of options to be able to give you quite a significant amount of control on the way that the nonlinear static parameters a nonlinear static study is run. Effectively, these are accessing parameters inside of the solver. The one area that I will point out to you is the convergence divergence area, where you're given the option to be able to choose what attributes you would like to converge for. In this case, the one thing to be aware of is never just use displacement on its own. Preferably, you should be choosing at least two of those options, whether it's load displacement, load and work and displacement, or potentially all three of them as well. So please be aware that if you are going to go into this environment, you're going to make some modifications, then the selection of these will dictate the accuracy of the results that you're getting. Another area that I'd like to point out to you is the surface contact settings. So one area that, one of the more difficult areas when transitioning from a static linear analysis to a static nonlinear analysis is the way the contacts are defined and the way that contacts play in the overall scheme of the success of running nonlinear analysis studies. The penetration type, in this case you're given the option of having symmetric or unsymmetric. So if you're trying to understand those a little bit, let's firstly have a look at the difference between the master entity and the slave entity. And you'll see the master and the slave entity are actually placed on the left-hand bottom corner. You've got your master option and your slave option for any of those contacting surfaces. If we have a quick look at the interaction and the way that they play with one another, the way that you define them depicts on the way that they will interact with one another. So you can see here that in this example we're using unsymmetric contact settings, and we have defined the parts in the context of the green being the slave and the blue being the master. So you can see here that the blue being the master, when a node of the slave comes into contact with it, it recognizes contact in that instance. If we switch around the master and the slave, you'll see in this case, with the blue being the slave now and the master being the green, we get a different set of contact results, whereby the node is now no longer penetrating through the design and is actually being detected as it comes into contact with the surface. So it's important that if you are using unsymmetric contact, to ensure that you recognize the difference between the two options selected in this instance. The best way of solving this is to use symmetric contact, which is going to ensure that it doesn't matter whether the master or the slave is selected, that it will be looking in both instances. It will be looking for nodes that are contacting the surface of the opposing part and vice versa. So keep that in mind when defining your contact settings. Activation distance, the maximum activation distance, and I'm often asked what we should be doing here. And in this instance, I'd like to highlight to you the way that the activation distance is defined. So if you were to check the maximum activation distance, you note there that you're given an option to define a millimeter measurement. In this instance, what it would be doing is it would be looking for an area around the perimeter of the node for contact. And you'll see here that in this instance we've got a box, and you can see a mesh that's been defined on the top of the box. And you can see one element, the largest square element, that's sitting on the top there. Now if we were to define the maximum activation distance as a measurement, then it would then use the elements at each point of, the nodes at each point of that element, would then, based on the measurement that we assign to it, just define a sphere around that element, and then using the boundary of that sphere, then it would put in place contact or look for contact with inside the bounds of that footprint. Now, if your parts are significantly moving, there's a lot of movement between components, recognize the contact outside of that boundary would not be recognized. This is a way of trying to limit the boundary or area in which the contact is actually looking for contact between faces. So it's trying to limit the extent to which it has to search for to specific areas. And as such, if you look at the various different maximum activation distance options, you can actually choose this in a number of different ways. You can, when the box is checked and no value is specified, so we can check the box here but not actually put in a value, the default solver distance will be used. And that's within inside of the parameters. Now, this is a large distance and it's based upon the model size. So the larger the model, the larger the distance that will be. When a value is input, obviously the solver will use that value, and when the box is unchecked, as it is in this instance, the auto function will be used, and using this setting the solver determines the activation distance. So there's a number of different ways that you can use this, this option. Okay, so what about parameters? One area we really haven't talked about in the previous webinars is parameters inside of Nastran InCAD. We're going to go over them in a little bit more detail today. So parameters is located right down towards the bottom of the Autodesk Nastran model tree. And by accessing this, we're given the ability to be able to modify the way that the studies are created and then solved. And this can be study specific. You'll see there's a number of different parameters associated to specific studies, like a nonlinear frequency and transient. But then you'll get some that are more generic, such as the output control, the memory management, file management, and the likes. So there's a number of options here for setting up and running a nonlinear analysis. You can modify these. And how do you know what you're modifying? Well, one of the best places to look is the Nastran reference manual. You'll find this, and I'll show you what this looks like a little bit later on. But you can find this by selecting the parameter that you're wanting to adjust as well. So you can see here that we've highlighted the S-line max act dist. If you click that word in the parameter box, it will actually bring up the description of what that parameter is, give you the type and the default value for each of those. Make note though that when you are modifying these, that some require a real value and others require an integer. So in some instances you will be required to put in 1.0, or in other instances 1. How do you know? Well, 1, you can look inside the reference manual, which will give you an idea. But probably one of the easier ways, you can see that the box around our input area is actually shown in red, and it won't allow us to exit this environment until we've placed the right value in. So in this instance, if 1 is not the correct value, then you can try typing 1.0, which would be the correct value, and hopefully allow you to exit that dialog box. So let's have a look at a couple of these parameters. The first one that I'd like to point out is the linear contact parameter. This parameter is great for troubleshooting models when you're transitioning a study from a linear static over to a nonlinear static. There's really two states of using this one. On, which it assumes that the contacts that they've already been defined. It's just taking the behaviors of those contacts and using them the way that you would previously define them. Now, as we said, one of the areas of difficulty in transitioning to a nonlinear study is contacts. So if you are having problems and you potentially think that it could be contact related, you can potentially turn this to off, in which case what it does is it overrides the default behaviors that you've defined in the contacts, and it defines all of those as a bonded contact. So it overrides those contacts temporarily, recognizing that you can switch these on and off to see whether they're having an effect as well. So if you're trying to troubleshoot and understand maybe it is a contact, potentially you could come in, turn this option on, check to see whether the study will solve and the results of running that, and then if it gives you the outcome that you want, turn it back off, and then you can recognize, well, it's helped me identify an area of my model or my setup that needs to be addressed. The second parameter that I'd like to point to you to is a nonlinear solution. It's S-line slide type. Now this has got two options, dynamic, which is the default, and it's really meant for fast moving parts, where you've got a lot of movement between the contacts of components. And how do you define fast movement? Well, it's probably where you're thinking, or need to consider the number of elements that are moving in relation to one another per increment. Remembering a nonlinear study is broken up into increments. So consider that 2, 3 or more elements moving per increment would be a dynamic study. A static analysis has much slower or much lower displacement, and as such you could consider that the elements moving in comparison to one another per increment is going to be small. one or maybe two at the most. One way of determining whether this is you need to look at this parameter or not is if you're getting spotty stresses in your contact results, try switching this setting to static to see whether this might solve those issues. Or it might at least indicate to you that maybe the contacts that have been defined need to be looked at and addressed. The next one is contact stab, and maybe as the name suggests here, this is around stabilizing the contact, and it's a parameter that does that. So on each contact surface, and contact surfaces only, it's going to add very weak springs to hold the surfaces in place. And it holds them in place just until contact. It's great for getting rid of instability in your model, where your model may not necessarily be converging, and for holding those contacts temporarily in place until that, like I said, that contact occurs. You'll note that the stiffness ramps down over subsequent iterations. So the consequence of using this should be marginal in your overall results. Another nonlinear solution parameter is LG-disp. LG-disp can be disabled using, and LG-disp is the large displacement parameter really. And you've got an option to turn large displacement on or off when you're defining the nonlinear study as well. But this can be changed directly inside the parameters environment. So turning off this using a 0 value effectively then means that large displacement, differential stiffness, and the follower forces won't be taken into account when you're running the analysis. So that's something to keep in mind as well. Another one is nonlinear. Another nonlinear solution parameters is NLK diagafact, and this is where similar to contact stability or contact stab, which adds stiffness to the contact surfaces. This will add a small amount of stiffness across the entire model. Okay, so not just to the surfaces that you've defined within inside your contact sets. Recognize though that the value that you use here should be very small. In this instance, recommendation is 1e to the minus 6 or smaller, and again this will ramp down over time and shouldn't significantly affect your overall result. The next one is nonlinear solution. Next nonlinear solution parameter is S-line stab KSFACT. And unlike the previous examples, which added stabilization using grounded springs, this parameter adds relative stiffness between the contact surfaces, again focused on stabilizing your contact sets. So the initial value, again, should be very small, and each iteration of that effectively halves the previous value. And the one thing to note here is that to make sure that you check your stabilization strain energy for the final increment to ensure that it's less than 1%, preferably the smaller the better. And then finally, before we move into having a look at this environment, let's just touch on some of the error messages. So these are some of the more common ones that you're likely to encounter, such as fatal error E5004, stiffness matrix, singular or non-positive definite. So this is definitely one of the most, if not the most common error message. It suggests the 0 on the diagonal on the stiffness matrix, and realistically what's happening is that there is infinite displacement of components. So effectively, if we look at the solution, there's a lack of constraints, or maybe it's the constraints have been improperly defined. There may be improperly defined contact between components and potentially singular elements as well. So realistically, the two areas that you primarily would go back is, have I defined my constraints, and how have I defined my contacts, and are they sufficient to constrain the part? The next error message is the fatal error T2135, unable to generate surface contact using specific parameters. And this in many ways is somewhat self-explanatory. It's actually saying to you reasonably clearly in the error message there that it's around the surface contacts not being properly specified. So maybe it's because of the way that the part or the contact has been defined. Maybe you use mid-surfacing of thin-walled structures to define the geometry, but for one reason or another, the contacts aren't defined correctly in relation to one another. Realistically, what this is doing is telling you to go back and look at those contact surfaces, look to ensure that the contacts have been defined correctly, and then to rerun and check them. And then finally, there's a range of other error messages that you get, E5078, 5077, and 5049. And realistically, what this is it means that the model is iterating but not converging before it gets to the maximum number of bisections, in which case what it does when it reaches the maximum number of bisections is kick up a fatal error. So again, this really comes back to looking at your model and making sure that it's stable. In this instance, go back and look at your contacts and constraints, which are a large focus of this webinar. So let's have a quick look inside of Nastran InCAD. Let me drag this over to our screen so you can see what I've got here. So we've set up a very simple study here. I'll go to Nastran so you can see it. Now we've only modelled half the part, and we use symmetry to define the other half of the part. And we can go inside of our Nastran InCAD environment and look at the study. So this is a linear static study. I'll point out the things that have been defined here. There's nothing special about setting up the study. Regardless of what's popped up over here. So we haven't set up any special settings in this instance. There's a contact that's been defined between the inside of the hole and the outside of the bolt. If we look at this, I've defined, as we said, a symmetric contact. You could define unsymmetric, recognizing that then you would need to take into account which one is the master and which one is the slave, and the consequence of doing that. And then we have this maximum activation distance, recognizing that we can go in here and change this if we wanted to. We can put in a parameter to define what the maximum activation distance would be. We can turn it off, in which case it would be auto, or we can use the max activation distance, which is a default in the system. So there's a number of ways of doing that. Also note that this is the area where we can come into and change some advanced parameters associated with the contact and the way that it's defined as well. We've defined solids, elements, and for our geometry. We have a load, and it's just a vertical load for 100 newtons, so around 10 kilograms. A force, I've fixed one side of the part, and then I've added symmetry. And symmetry is a constraint that we can quite quickly add. You can see here I've added symmetry in the Z direction and chosen the faces that need to be symmetrical, which is those three faces, and go OK. Beyond that, however, there's really nothing that needs to be done. We can just simply hit run, and the solver will then run off and solve this study. I'll wait for it to solve before I move into the next section. The good thing about running a linear analysis is it helps you very quickly and easily make sure that you've set up a lot of the things that we've talked about previously. Our contact, our constraints, our loads, make sure that we're, our mesh, we feel as though we're getting sufficient mesh in localized areas prior to running our a nonlinear analysis. Now this shouldn't take very long at all, hopefully. You can see here it's running through and solving the part. Contact convergence has happened. Nastran solution complete, and we should be able to look at the results of this study. And you can see here, as we would expect, that the bolt is shifting up. You're getting contact in the bottom left corner of the bolt. You're getting contact at the top right or midway along the top edge of the bolt. And the reason why you're seeing interference there is possibly because of the scale that we've used in the displacement. You can change that by going into Edit, Deform options, turn that to actual rather than a percent, and that will actually change it to, or minimize it if you change the percent down to a smaller or larger value. And we can animate these results to have a look and see what it's looking like as well. Now, recognizing with a linear analysis, it's only looking at the initial result and the final result, and then it's putting in place animation between there. So it's interpolating the results between the initial and final positions. Okay, so we've got our study set up. So often, like I said, this is the first point we start. Then we can duplicate this study. We could just modify the study, but in this instance, I'll duplicate it. I'll call this study 2. Okay, and you'll see that it's duplicated as a linear static study. Now, the good thing about using Nastran InCAD is that I can go in and I can quickly switch this study from a linear static to a nonlinear static study, which is what I'm able to do here. Now, a couple of things, or one thing, this is where a large displacement option is turned on by default, and we can turn it off if we wanted to. Like I said before, there's a parameter that's associated with the large displacement option that we can adjust if need be. What else do we need to do? Well, one of the more notable effects of changing to a nonlinear static is that under the subcase now, we get a nonlinear setup. So if we enter this environment, you can see here that we have the number of increments, the intermediate output, and the arc length. This is what we talked about a little earlier. So we can go and turn on intermediate output, which will give us, after each iteration, or each increment, a set of results, and that'll happen dynamically as it's being solved as well. The other thing we can do is adjust the increment number. So if we want more or less, we can do that here. But the one thing you can do, and I didn't know about until recently, is the fact that you can actually remove this number altogether, in which case it will automatically then solve for that. So the solver will take that into account and automatically increment the part. So that's a nice little tip. Okay. Beyond that, there's not a great deal else that we need to do before running our study. But what happens if we got into a problem with our analysis? Now, I'm not going to try and force a problem here, but what I am going to do is show you that the parameters dialog box. So if we come down to the parameter dialog box, I edit this. This is the environment that I can come into and modify some of the values and variables that we were talking about a little bit earlier. So you'll see here that we've got the nonlinear solution option here, and here are the various parameters that we can come into and adjust. Contact stab. Remember, we could go from auto in this case. We've got large displacement on or off, so we can adjust those as well. If I wanted to, I can come down to S-line slide tip. I can change this to static, and then I can put in a value, recognizing that the value that I need to input needs to meet the criteria of the box. You can see here there's a red outline around the outside of the box because I don't have the right value. In this case, I need to make sure that I put in at least the point, okay, 0.0 in this case. So you can see here that I can go through and modify any of these values. Now, what happens if I'm trying to find what each of these values mean? Well, I can click on any of those, and what you didn't see is in the background it opened up in my web browser the Nastran website, and it's then gone to the nonlinear solution process parameters with inside the Nastran reference guide, and it's pulled up the S-line stab KS fact, and it's given me a description of what this is, what the type of value is that I need, and the default value that's in place in this instance. So you can see here that I can quite quickly go and find any number of parameters and what they specifically mean by simply clicking on those values there. So, I think that's about it for today. So let's quickly just shift back over into our presentation. Just want to make a quick acknowledgement before closing out the webinar. I want to thank Andrew Sardarelli, who's part of the technical support team. He's a technical support specialist working inside the simulation group, working for Autodesk. He's the one that actually presented the bulk of this presentation. So I'd like to thank Andrew for sharing that. As always, we're very reliant on the expertise of specific people inside of Autodesk and specific solutions. Andrew actually has quite a comprehensive webinar on this same topic, which goes into more detail and actually runs through solving a nonlinear analysis and looking at some of the issues and the more specific details. I would suggest, if you're wanting to find out some further information, that you actually do a quick Google search. You'll find Troubleshooting Nonlinear Analysis in Nastran InCAD on the YouTube website. You can also go to the Autodesk Simulation YouTube channel and find this webinar and a whole bunch of others as well for you. If you'd like further information about Nastran InCAD, please feel free to reach out to any of our authorised resellers. You can find them at autodesk.com.au/resellers. You can also find some information around Nastran InCAD by going to the autodesk.com website, and again, my details there if you need to get in contact with me. Otherwise, I will say thank you for your time today. It's not such good weather here in Melbourne today. Hopefully we see it turn for the better soon. Enjoy your day, and as I said, any questions, feel free to reach out to me, but otherwise, have a good day. Bye for now.